long before visitors witness towering geysers launching boiling water into the air or hear the rumble of distant waterfalls echoing across Yellowstone National Park. Another force is constantly at work beneath the forests, rivers, and volcanic plateaus. Most of the time, it remains almost invisible, revealing its presence only through tiny tremors that ripple across the landscape. Individually, these earthquakes are usually too small to attract widespread attention. Taken together, however, they can become one of the clearest windows into the restless geological engine powering one of the most closely watched volcanic systems on Earth. During the middle of July in the year 2026, scientists monitoring Yellowstone detected another increase in seismic activity as an earthquake swarm unfolded beneath the national park and its surrounding region. The most notable event measured a magnitude of 3.3 and occurred approximately 24 miles, or 39 kilometers, south-southeast of Mammoth, Wyoming. According to seismic data, the earthquake struck during the afternoon in Coordinated Universal Time on the 16th of July at a relatively shallow depth of approximately 4 miles, or 6.5 kilometers. While a magnitude 3.3 earthquake is considered moderate by Yellowstone standards and generally causes little or no structural damage, its occurrence as part of a larger swarm immediately drew the attention of geologists who continuously monitor the region. The location of the earthquake was particularly significant. Mammoth sits near the northern portion of Yellowstone National Park, an area that has experienced countless earthquakes over recorded history. Every tremor recorded there adds another piece to an enormous geological puzzle that scientists have spent decades trying to solve. Rather than focusing on a single earthquake, researchers pay close attention to the pattern developing around it. In Yellowstone, patterns often reveal much more than individual events. Unlike many earthquakes that occur along well-defined tectonic plate boundaries, Yellowstone's seismic activity originates from an intricate combination of volcanic processes, crustal deformation, underground fluid movement, and regional tectonic forces. These interacting systems produce one of the highest rates of seismicity anywhere in the United States. Hundreds to thousands of earthquakes are detected in and around Yellowstone every year, although the overwhelming majority are far too small to be noticed without sophisticated instruments. The latest swarm quickly became another reminder that Yellowstone is not a dormant landscape frozen in time. Instead, it is an evolving volcanic system whose underground plumbing continues to shift, expand, contract, and circulate enormous quantities of heat and fluids. Every earthquake provides scientists with valuable information about conditions occurring several miles beneath the surface, where direct observation remains impossible. Earthquake swarms differ considerably from the earthquake sequences most people are familiar with. In many tectonic settings, one large earthquake is followed by progressively smaller aftershocks as accumulated stress gradually dissipates. Yellowstone often behaves differently. Swarms consist of clusters of earthquakes occurring within a relatively confined area over periods ranging from hours to weeks or even months, without a single dominant main shock controlling the sequence. These swarms may involve dozens, hundreds, or even thousands of individual earthquakes. Most remain extremely small, often measuring below magnitude 1 or even registering negative magnitudes detectable only by sensitive seismic equipment. Occasionally, however, stronger earthquakes emerge within the swarm, drawing public attention and raising questions about whether larger geological events may be developing beneath the park. For Yellowstone scientists, earthquake swarms are not unusual occurrences. In fact, they represent approximately 1/2 of all seismic activity recorded within the Yellowstone region. This statistic alone distinguishes Yellowstone from many other seismically active regions around the world. Swarms have become such a defining characteristic of the park that researchers now study them as one of the primary indicators of underground geological processes. Understanding why Yellowstone experiences so many swarms requires looking far deeper than the park's forests, lakes, and geothermal basins. Yellowstone occupies the surface expression of an immense volcanic system fueled by heat rising from deep within Earth's interior. Unlike volcanoes located along plate boundaries, Yellowstone sits above a long-lived mantle hotspot, As the North American tectonic plate slowly moves southwestward over millions of years, the hotspot has produced a chain of ancient volcanic centers stretching across southern Idaho before reaching its present location beneath northwestern Wyoming. This hotspot supplies extraordinary amounts of heat into the lower crust, where large reservoirs of partially molten rock reside. Contrary to popular imagination, these reservoirs are not gigantic underground lakes filled entirely with liquid magma waiting to erupt. Modern geophysical imaging has revealed something much more complex. The crust beneath Yellowstone contains vast regions composed primarily of solid rock interspersed with pockets of molten material, superheated fluids, and gases. These partially molten zones behave differently from completely solid rock, influencing stress distribution throughout the crust. Above these magma storage regions lies an extensive hydrothermal system unlike any other on Earth. Thousands of geysers, hot springs, fumaroles, mud pots, and steam vents continuously release heat escaping from underground. Water circulates through fractures extending deep into heated rock before returning to the surface under immense pressure. This constant movement of hot fluids plays a critical role in Yellowstone's seismic activity. As water travels through underground fractures, pressure can build within confined spaces. Minerals dissolve and precipitate, fractures expand or seal, and stresses redistribute through surrounding rock. Eventually, enough pressure accumulates to overcome friction along existing faults or create new fractures. When that happens, earthquakes occur. Many Yellowstone earthquake swarms appear closely linked to this underground circulation of hydrothermal fluids. Rather than indicating large-scale magma movement, numerous swarms result from water and steam migrating through complex fracture networks. Scientists compare the process to pressure gradually building inside an elaborate system of underground plumbing. Every adjustment within that plumbing network may generate small earthquakes as surrounding rocks respond. The recent swarm near Mammoth fits within this broader geological framework. Although scientists continue analyzing incoming data, the depth and distribution of the earthquakes suggest activity occurring within the brittle upper crust, where faults, fractures, and hydrothermal circulation commonly interact. Determining the precise mechanism behind any individual swarm requires detailed analysis involving earthquake locations, waveforms, fault orientations, deformation measurements, and geothermal observations collected from numerous monitoring stations distributed throughout the park. Yellowstone remains among the most heavily instrumented volcanic systems anywhere on Earth. Networks of seismometers, continuously operating global positioning system stations, satellite radar observations, gas monitoring equipment, thermal imaging, stream gauges, and geological field surveys provide researchers with an extraordinary amount of information. These instruments operate around the clock, allowing scientists to detect even subtle changes occurring beneath the landscape. Each earthquake recorded during a swarm contributes another data point toward understanding the evolving conditions underground. When plotted together, earthquake locations often reveal hidden fault planes, migrating fluid pathways, or areas where stress is accumulating within the crust. Researchers examine whether earthquakes migrate systematically over time, remain tightly clustered, or spread across broader regions. Each pattern carries clues regarding the underlying geological processes. The magnitude 3.3 earthquake stood out primarily because it was large enough to be felt by some people in nearby areas, while remaining relatively modest from a geological perspective. Earthquakes of this size release considerably more energy than the tiny micro-earthquakes comprising much of Yellowstone's background seismicity, yet they remain far below the magnitudes associated with destructive tectonic earthquakes elsewhere in the western United States. Residents and visitors occasionally report brief shaking during such events. Windows may rattle lightly, hanging objects may sway, and those indoors may notice a quick jolt lasting only a few seconds. Within Yellowstone itself, wildlife often continues undisturbed after these minor earthquakes, although researchers have documented instances where animals briefly alter their behavior following noticeable seismic events. Despite their generally modest size, earthquake swarms often generate significant public concern because Yellowstone's name has become synonymous with the idea of a supervolcano. Images of catastrophic eruptions have captured public imagination for decades, leading many people to assume that any increase in earthquake activity signals an imminent volcanic disaster.
Scientists consistently emphasize that this interpretation is unsupported by available evidence. Earthquake swarms occur frequently within Yellowstone without leading to volcanic eruptions. In fact, historical monitoring demonstrates that swarms represent an ordinary component of the park's ongoing geological behavior.
That conclusion rests upon decades of continuous observations. Yellowstone has experienced numerous swarms involving hundreds or even thousands of earthquakes during modern monitoring. Some have persisted for weeks before gradually fading away. Others have migrated across different portions of the caldera or concentrated along existing fault systems. Nearly all eventually declined without producing volcanic eruptions. Even so, scientists never dismiss earthquake swarms as unimportant. Instead, every swarm receives careful examination because it provides opportunities to observe processes unfolding deep underground. Comparing new swarms with previous events helps researchers refine computer models describing Yellowstone's evolving volcanic system. Adding another layer of scientific interest to the recent activity is the ongoing deformation of Yellowstone's surface. Over many years, researchers have documented repeated cycles during which portions of the caldera slowly rise before later subsiding. These changes occur gradually, often amounting to only a few inches or several centimeters over periods spanning months or years. Yet such seemingly small movements reveal enormous geological forces operating beneath the surface. Ground uplift has become one of Yellowstone's defining characteristics during modern scientific monitoring. Sophisticated global positioning system receivers anchored directly into bedrock detect movements far smaller than the thickness of a human fingernail. Satellite-based interferometric synthetic aperture radar, commonly known as INSAR, complements these ground instruments by measuring subtle changes in surface elevation across broad areas with remarkable precision. Observations collected over recent decades reveal that Yellowstone's surface behaves almost like a slowly breathing landscape. Certain regions gradually inflate before relaxing again through periods of subsidence. Rather than moving steadily upward or downward, the caldera alternates between expansion and contraction as conditions evolve within the underlying volcanic and hydrothermal systems. The present period of uplift has therefore attracted close scientific attention alongside the developing earthquake swarm. Researchers do not examine these observations separately. Instead, they seek relationships between seismic activity, deformation, geothermal changes, gas emissions, and regional stress patterns to determine whether all represent components of a common geological process. One explanation involves increasing pressure generated by hydrothermal fluids circulating through fractured rock beneath the caldera. As superheated water accumulates within underground reservoirs, surrounding rocks may slowly expand. This expansion produces measurable uplift at the surface, while simultaneously increasing stress along nearby faults capable of generating earthquake swarms. Another possibility involves modest movement of magma at considerable depth. Scientists emphasize that magma migration does not necessarily imply an impending eruption. Magma frequently shifts within underground reservoirs without approaching the surface. Small redistributions of molten material may alter pressure enough to produce gradual uplift while remaining entirely contained within the deeper crust. Distinguishing between these possibilities remains one of the central challenges facing Yellowstone researchers. Each new earthquake, every centimeter of uplift, and every geothermal measurement contributes additional evidence toward understanding which processes dominate at any given time. Rather than indicating instability alone, Yellowstone's current activity demonstrates the remarkable complexity of one of Earth's most dynamic volcanic systems. Hidden beneath forests filled with bison, wolves, elk, and towering lodgepole pines lies an immense engine powered by heat that has shaped the landscape for millions of years. Every earthquake swarm reminds scientists that although the scenery above appears timeless, the forces below remain continuously active, reshaping the crust through countless subtle adjustments that rarely capture public attention until a stronger tremor briefly interrupts the quiet. The ongoing ground uplift observed across portions of Yellowstone provides another critical piece of evidence that scientists examine alongside earthquake swarms. On its own, uplift does not automatically signal that an eruption is approaching. Combined with seismic activity, however, it becomes part of a much larger picture describing the changing conditions inside one of Earth's most complex volcanic systems. Every millimeter, or fraction of an inch, of vertical movement represents an adjustment taking place several miles beneath the surface, where heat, pressure, rock, and fluids interact continuously. Modern technology has transformed the way Yellowstone is monitored. Decades ago, scientists relied primarily on seismometers and field observations. Today, an extensive network of continuously operating global positioning system stations measures movements of the Earth's surface with astonishing precision. Instruments permanently anchored into solid bedrock can detect changes measured in mere millimeters, allowing researchers to determine whether sections of the caldera are rising, sinking, or remaining stable over long periods. These ground observations are complemented by satellites orbiting hundreds of miles, or several hundred kilometers, above Earth. Using a technique known as interferometric synthetic aperture radar, scientists compare repeated radar images collected over weeks, months, and years. Tiny differences between successive satellite passes reveal whether the landscape has risen or fallen. Even changes far too small for people to notice become clearly visible when viewed through these sophisticated measurements. Yellowstone has displayed repeated cycles of uplift and subsidence throughout the modern monitoring era. During some periods, the caldera floor rises several inches, or several centimeters, over a span of a few years before gradually reversing direction and settling downward again. These cycles resemble the slow breathing of the volcanic system, reflecting changes occurring deep underground rather than dramatic movements visible at the surface. Understanding the source of this deformation remains one of the most fascinating challenges in volcanology. Scientists generally recognize that no single mechanism explains every episode of uplift. Instead, Yellowstone appears to respond to several overlapping geological processes occurring simultaneously. One major contributor involves the enormous hydrothermal system that powers Yellowstone's world-famous geysers and hot springs. Rainwater and melting snow gradually seep into fractures within the volcanic rocks before descending thousands of feet or hundreds of meters into increasingly hotter environments. As the water approaches intensely heated rock, temperatures climb dramatically while pressure prevents the water from immediately boiling. Eventually, this superheated water begins rising through an intricate network of cracks and underground reservoirs. Along the way, it dissolves minerals, transports dissolved gases, alters surrounding rock, and redistributes heat throughout the upper crust. Changes in fluid pressure can force existing fractures to widen while opening entirely new pathways. Every adjustment modifies the stresses acting on nearby faults. When pressure exceeds the strength of surrounding rock, small fractures develop, or older faults slip by tiny amounts. These movements release accumulated energy as earthquakes. Rather than resulting from massive tectonic forces alone, many Yellowstone earthquakes originate because underground water and steam continually reorganize the hydrothermal plumbing system. This relationship explains why earthquake swarms frequently occur near geothermal regions. The migration of hot fluids often progresses gradually through interconnected fractures, producing clusters of earthquakes that appear to move across the landscape over time. Scientists have documented several Yellowstone swarms whose earthquake locations migrated systematically, strongly suggesting the movement of pressurized fluids beneath the surface. The current swarm, occurring south-southeast of Mammoth, may reflect similar processes. Researchers are carefully analyzing whether the earthquake hypocenters display any directional migration, clustering, or depth changes that might indicate underground fluid movement. These details help distinguish hydrothermal activity from deeper magmatic processes. At greater depths, another source of uplift becomes increasingly important. Yellowstone's magma storage system extends through a broad volume of crust rather than existing as a single enormous chamber filled entirely with molten rock. Advanced seismic tomography, which functions much like a medical CT scan of the Earth, has revealed that much of this underground reservoir consists primarily of solid crystalline rock containing interconnected pockets of partially molten material. This discovery significantly changed scientific understanding of Yellowstone. Earlier public perception often imagined a gigantic underground lake of liquid magma ready to erupt. Modern imaging presents a far more complicated reality. Only a fraction of the reservoir exists in molten form, while the surrounding framework remains largely solid. The partially molten material behaves more like a crystal-rich mixture than freely flowing lava. Even within this partially molten environment, pressure changes can occur. Fresh magma rising slowly from deeper portions of the mantle may enter the lower crust, increasing pressure without approaching the surface. Existing magma bodies may redistribute internally as temperature, gas content, and crystallization evolve over time. These adjustments can gently lift portions of the overlying crust while remaining entirely confined several miles underground. Scientists therefore examine uplift alongside numerous additional observations before drawing conclusions. If magma were rising rapidly toward the surface, researchers would expect to observe several independent warning signs occurring together. Earthquake activity would likely intensify substantially. Earthquakes might migrate steadily upward through the crust. Ground deformation would probably accelerate rather than continue at relatively modest rates. Gas emissions, particularly carbon dioxide and sulfur dioxide, would likely change noticeably. Hydrothermal features could exhibit significant alterations in temperature, chemistry, or discharge rates. To date, Yellowstone's monitoring network has not identified this combination of escalating indicators. Instead, current observations remain consistent with the dynamic but relatively stable behavior that has characterized the volcanic system for decades. Earthquake swarms continue to occur periodically, uplift alternates with subsidence, and geothermal activity evolves gradually within expected ranges. Historical records reinforce this interpretation. Yellowstone has experienced numerous episodes during which earthquake swarms coincided with measurable uplift. In many cases, both eventually diminished without progressing toward volcanic unrest. These recurring cycles demonstrate that the volcanic system naturally undergoes periods of adjustment as heat and fluids redistribute beneath the caldera. This does not mean scientists become complacent. Quite the opposite. Yellowstone represents one of the most intensively monitored volcanoes anywhere in the world, precisely because researchers recognize its enormous geological significance. Every earthquake, every centimeter of uplift, every gas sample, and every thermal measurement contributes to an expanding database that improves forecasting capabilities. The value of continuous monitoring extends beyond Yellowstone itself. Similar techniques are now applied at volcanoes across the globe, helping scientists recognize subtle warning signs before hazardous eruptions. Lessons learned in Yellowstone strengthen volcanic hazard assessments from Alaska to Iceland, from Japan to New Zealand, making this remarkable landscape an invaluable natural laboratory for Earth science.